So welcome back, everybody. A warm welcome to both of you online and those of you here. So today, the main topic is us going through the basic mathematics and the different parameters which we get for a convolutional neural network. Now, last week, one of the things which we did was to give a short introduction to CNNs, convolutional neural networks. But today we are going to repeat some of the topics we discussed in the second half of the lecture last week. And we are going to revisit this basic structure. And we're also going to look at the way we are going to do the mathematics of convolution, because that becomes important if you want to write your own code. Now, in the lecture notes this week, you will find examples on how you can implement a CNN with a TensorFlow, or using PyTorch, or writing your own code. So most likely we will spend time also next week on discussing how we can write our own code. So there are always project groups who want to write their own code from scratch. And this is typically just a one semester project to write a CNN. And I wanted first to go through the mathematics, because then you can see how you can write your own code. But this is also important because then you understand what are the input values to TensorFlow or PyTorch, so that when you see some of these input variables, you have a deeper understanding of what they actually mean. So the main aim today is actually to go through the basic mathematics of CNNs. We are going to slow down the pace and use mainly the whiteboard, but you will find most of the information here in the slides as well. And when we go through the setup of our own code, we are going to use what we discussed last week in connection with neural networks, because a CNN has somewhere in its end part a normal neural network. So much of the basic machinery which you've seen with neural networks is something which we will repeat. But at the same time, we need to implement the process of convolution. And then, as we discussed last week, we have this detector stage or reload stage. We have something called pooling, which we also need to discuss a little bit. And then we have additional hyperparameters like stride, we have padding, and the size of the filters, etc., etc. So we need to have a clear view of what are the parameters which define a CNN. And coming back to the projects, so one thing which I wanted to do when we are done with today's lecture, because I know that some of you would like to give a presentation after the break. That means in the exercise session about projects like we had last week. But I wanted to send an email to all of you, because now we have a rough picture of who wants to do what. And so if somebody wants to get in touch with other people doing physics-informed neural networks, we can put people together. So I'm just going to send a list of all the projects which you have defined and which I have received through email. Some of these projects are also available online. So if you want to look at them, feel free to do so. And if you go to the course page, so if you do that, so let's go to the course folder. And there is a folder which I wanted to remind you of. If you go to projects, you will find one which has project examples. And these are examples from last year. And the names, they say obviously what they are about. There was a group who wrote a CNN code, people who did the Hamiltonian pins. There was a group which did recurrent neural networks with long short-term memory. There was a plain pin groups. There was another group which did RNNs, but based on as input to language modeling. And then there was a project on bioscience using convolutional neural networks and other methods. So these are examples which you can look up. But then if you go into 2025, you will find project proposals. And as of now, we have 4 groups who made presentations last week, so you can take a look at them. So there is one on large language models. Simon has one on quantum mechanics, There's one on deep reinforcement learning and pins for solving differential equations. And then we have the project of Oda and Parham on using machine learning methods for problems in bioscience. And this is the one which you have here, FYS5429. And for those of you who are interested, take a look at them. And if you would like to join them, I mean, just shoot them an email. Is that okay? So if you want to, you can send me. I mean, this is just something like 1, 2, 3 slides. It doesn't need to be pretentious, but then people can also see what your ideas are. In addition to me just sending you just a short paragraph that this group is doing that and this group is doing that. Okay? So feel free to send me just 1, 2, 3 slides or just a short paragraph of what you're planning to do. So I already have some of them, but if you haven't done so, just try to do that by the end of the week. And then I will try to send an email to everybody about all the different projects which we have and project groups. And most project groups do accept other people. They actually are looking after partners. So a typical size of a group is 2 to 4 people, which is often very, normally allows for pretty efficient sharing of the load. And you can decide whether you want to write just one project in case you're dealing with the same themes, because then it would be natural to, instead of just repeating yourself in the second project because you make an extension, just to have one long project. But this is very much up to you folks. But irrespective of that, we want a summary report by the March the 21st. So we know what people are. So let's go back to the material here. You will also find the typical reading recommendations, and the background material is pretty well covered by the text by Goodfellow et al., and you can access that online. But then you also have Rashka's text in chapter 14, where you have access to the Jupyter notebooks and codes in PyTorch. In the lecture notes, which I have, there is a code example using PyTorch, and you're going to see this data set, boring MNIST data set again and again, because that's a data set I've been using in many cases. Actually, it's nothing bad in using the MNIST data set in your own implementations, because that's a kind of benchmark data set in the literature. And then we have these other textbooks by David Foster and Joseph Babcock and Raghav Bali, which are also pretty good ones. And they have Jupyter notebooks as well, which you can download and study. So there's a lot of information here. And I hope it's not too confusing. And then there are some videos, some other reminders about these different textbooks, etc., etc. So what I want to do now is actually just to switch over to the whiteboard and slowly go through the basic ingredients which we need to think of when we want to look at a convolutional neural network and how we're going to set it up and what are the parameters. Any questions so far? It's okay if I just switch to the whiteboard? So sometimes it's okay to just do that, because just watching slides, I mean, is going to put you guys asleep. Actually, during COVID, when I was teaching towards the US, there was a student on the feedback which said that it's a very nice way of saying that you have a boring voice, because when she was stressed, she would watch the videos of the lectures, and then she felt she could relax and most likely just fell asleep. Okay. So if we now look at CNNs, so let's repeat the basic ingredients. And then we are going to list the kind of hyperparameters which you're going to encounter. Now, there is a first step which can contain one or many convolutions. So I'm just going to write several convolutions. So this is normally what we call the convolutional stage. This is the mathematical process of convolution, and I'm going to describe that in more detail a little bit later, what that actually means through examples. so that you have a feeling of what it means and how you implement it in the most efficient way in your own program. So we have several convolutional in parallel. This can be done in parallel because we are typically scaling down an image. So you could have an initial image, which looks like this. So it could be an image which has, let's say, 28 times 28 pixels. And it could have 3 colors or just a black and white one. So we call these color channels. So if you have just one color channel, we just put 1. So this is the typical size of the image. And then what is often done then is to scale down the size of this image by applying filters. And these filters are often handmade for the specific type of problem. And you will see that there's a lot of discussions in the literature, what kind of filters are best for these and these problems. In general, CNNs have had a huge success in applications to imaging, recognition of images, etc. But it's also being used now for regression type of problems. It's normally applied to what we would call a supervised learning problem. That means that the data are often labeled, an image of a cat, an image of a dog, etc. So the typical process here is that there is a filter. So we can take a small part of the image and we can make a new image, which is a scaled down one, which is smaller. So in here, we are applying a filter, but we can actually apply this many times. So we can make several copies. You see my drawing skills are actually not very good. So you can make many copies, many scaled down copies. Because it's pretty common to actually not do only one, but to do many of these, because then you have several samples of the image which are taken care of. And you can scale this down according to specific properties. So if you have an image of a house, you will take care of the corners, where the roof is, where the windows are, etc. And these scaled down images can then be rescaled down again, so you can have more such types of convolutions later. But it's often done through several convolutions in parallel, so that's the first step. Then the parameters, so these filters have parameters, and these parameters are trained by backpropagations. To be trained in the filter, trained by backpropagation. Then the next stage is that the output from this convolutional stage is then sent through what we normally call a detector stage. This means that actually what you're doing is that you're sending it through an activation function, which can be of the type of ReLO, it could be an ELO, etc. And what you would often do then is to use this as a further downscaling. And you would often just take perhaps the largest values which are produced by a specific part of the image. So that's one further possibility to downscale. So it's often called a detector stage or just a ReLO stage, because many people use the ReLO activation function, but you don't need to use the ReLO function, activation stage. And there you can scale down further the image by just keeping the largest values in the small region. So if you go back to the previous image which you had here, you can think of what happens here, that this takes a part of your image, this one takes another part of the image, and then you're making replicas which contain some selected features, and then you grind this through a ReLO function, an activation function, and there you can then spit out only the largest values of the different pixels which you're keeping, for instance. Now, this case here does not have trainable parameters, but only hyperparameters which define the ReLU function and how you want to scale down the image further. So only hyperparameters, which you are setting up at the beginning of the calculation. So these are parameters which are not trained by backpropagation. Then the final stage, which is called normally pooling stage, you can do a further downscaling. And we are coming back to this one. So the pooling stage is normally done by something which is called max pooling. And then you would pick the largest value in a specific region, or what is called average pooling. So you could take a region of your image and you can just take the average of all the values which you have. So this is a way to scale down, again, scale further down the image, or the data set which you have. Then there is the next stage, which we normally call for a flattening. Stage plus an NN stage. So that means you just flatten your data to just one long array, and you feed this in to a neural network. And there you do the training again. So the neural network could then have 1, 2, 3 layers. So you see immediately that everything here can get pretty deep when it comes to the type of layers you can add to the system. So like this stage 1, 2, 3, which normally is defined as a convolution part, as a container, that is something you can repeat many times. And if you go to one of these big trained networks like ImageNet, they have something like 10 or something like that convolution stages. And then they can have neural networks with 4 to 5 layers. So these are really deep networks which need a lot of computational resources to train. So, and here, the pooling stage has only hyperparameters. Let me just remind you of that, hyperparameters. And that is then part of the architecture of your network. So the architecture is your model. Just keep that in mind. And then here we would train weights and biases with backpropagation again. So if we want to make an image of such a neural network, you could now just make a drawing which looks like this. So let's just wait a little bit so everybody has been able to write it down. So if you want to make an image, you would then have an input layer. So this is your original image, and that feeds into, and suppose now that we have only one convolution part. So we just call this the convolution part, but you can repeat this, because often what people do is that they make one convolution. You produce, for instance, 10 images which have been scaled down through a filter, and then you run through with pooling at the end, and then you feed this into a new convolution stage where you scale the images further down. You can make more replicas so that the images at the end are much smaller than the original one. And as I said, if you have a professional image with, let's say, 200 times 200 pixels, that means that you need something like 40,000 input nodes. And that's a huge dimensionality. And if you think of a neural network where you do the affine transformations and you have, let's say, 100 nodes in the first hidden layer, that means that you have a dimensionality of 40,000 times 100 of the weights to train. So that's a huge problem. But if you can reduce that problem to many smaller images, then with smaller size, that reduces the computational complexity of the problem. So the convolution stage has then, and let's just mark them in red here. So there's one part which I just called for the convolution, conv. So that's the mathematical convolution where you have parameters you need to train. This feeds in to what we call this detector stage, or which I'm going to call the ReLU stage. Since in most applications you use the ReLU function, but you can actually change that. You're not limited to that, but this was one of the first activation functions which was used. And then we have the so-called pooling stage. Pooling. Now, this feeds into the next stage, where you would flatten the data, plus run it through a standard neural network. And this neural network can be a deep neural network. And then this produces an output. The output is then fed into your cost function or loss function. So cost, loss. And then it's compared with your data. So these are the target values you want to compare with. This is the basic structure of a convolutional neural network. So for those of you who are going to, and actually many of you who want to use CNNs in the project to recognize images, this is something you would have to set up as a basic architecture. So let's now try to look at what is going on behind the curtains here, so that we can see all the hyperparameters which you need to define when you're setting up either TensorFlow or PyTorch or writing your own code. And as usual, I mean, feel free to use the path which makes you most efficient. So if you want to use PyTorch, you use that. TensorFlow, you use that, etc. So let's now look at examples here, so that we can see how different parameters pop up. So we are going now to focus on the convolution stage first. And let's take an input. So we have an input X. So this is something we would then represent as a matrix. Suppose it's an image with 3 pixels. So that's a 3 times 3 matrix. And I'm just going to put in the slots here. So we have X00, X01, X02, 11, X12, and then we have X20, X21, and X22. This is the input, and now we have a filter. So we are going to take a filter, which is a 2x2 filter. So we call this is a convolutional filter, W. And this is going to have 4 elements. So these are the elements we want to train. So the W's which you see here become trainable parameters. So we have a W01 and W10 and W11. Now this is going to give us a 2x2 object. And you will see how this actually takes place. So mathematically, we are coming back to the definition of convolution. But what you end up doing now is producing a final 2x2 matrix. So this is a 2x2. This is a 3x3 input matrix. And one of the reasons why I do this now is that later we are going to see how we are going to encode this in an efficient way. So that's important when we want to write our own codes here. So let's just split it up. Now, the first part we do now, since we are going to have 2x2 matrices, we want to filter things through. We are going to take the first 2x2 block, which is this one, that block. And that is going to give us, when we do convolution now, X00 times W00 plus X01 times W01, X10 times W10 plus X11 times W11. So what I'm applying now is the mathematical process of convolution. Now you can think of convolution is used a lot, especially if you're dealing with problems from imaging and filtering. So if you have a data set where you record, let's say, how a satellite is moving, and then in the beginning, the movement of the satellite, when you recorded it, was pretty noisy. So you had lots of fluctuations, and you cannot determine exactly where the satellite is. And then after some time, your data become very nice. So what you could do then is actually filter out the data which was noisy. So you would often apply this type of procedure to data which have perhaps a lot of noise, and you want to filter that away. And there are processes of doing that mathematically, which we are going to see more formally now. But what you see now is that I am multiplying each element here with an element in the filter, and that produces a final element. So the next thing I'm going to do now is actually to move to this block. And that block is going to give me x01 multiplied with 0, 0, plus x02 multiplied with 0.1. And then I have x11 multiplied with w10 plus x12 multiplied with w11. Okay? So the what I've done now is to move just one column. So if you notice this one, I just moved one column here. So this is called stride equal to 1. So S is a parameter which is called stride. So when I perform this multiplication, I could actually not jump with one column or one row, but I could jump with 2, 3, etc. That becomes a parameter in the way I filter out information. This is a hyperparameter. An additional parameter you need to set in the architecture of the network, because it has to do with the way you actually filter away information. Yeah?
How do you find the values of the W's?
Oh, the value of W's are trained by backpropagation. So these become your parameters. So you would have to do backpropagation in the neural network part, but you also use backpropagation in the filter here. So these are trainable parameters. You would typically initialize them with some normal distributed weights, which are small values. There is also a bias you have to plug in here. So you see now that this proceeds in a pretty straightforward way. So now we went through the columns. Now we step one row down. So that means that we are going to take this block, that one. And if I take that block, I'm going to fill in, so I'm just going to use the x1 0 multiplied with w00 plus x11 multiplied with w01. And then we have plus x20 multiplied with w10 plus x21 multiplied with w11. And then I can now move again one step to the right, one column. And that means that the final one is now simply going to be given by this one multiplied with the different elements which you have here. So that's going to give me now x11 multiplied with w00 plus x12 multiplied with w01, x21 multiplied with w10 plus x22 multiplied with w11. Now, if you now look at this operation here, yeah?
Stride?
Yeah, also down, yeah, yes. So when you set the stride the same for columns and rows. You have to actually look carefully at the matrix you have, because this means that if you have a matrix which doesn't match it, so if I were to take stride 2 here, in my next time when I do it, I wouldn't have a 2x2 matrix. So stride 2 is not possible here. But if I had set up a 4x4 matrix, then I could have had stride equal to 2 and stride equal to 1. So this is just something you have to look at with respect to your input data, so that the stride actually matches the dimensionalities. Because the filter is actually the one which decides which blocks of the matrix you're taking out. And every time you do this, you can actually use this again and again. And you could think now that your image could be a larger matrix itself. So you could think of this as just a fraction of your image. And you're taking that fraction and filtering it down. And then you're making new replicas. So at the end, you have made many replicas, which then contain information from everywhere in your image, but you have downsized them. So now you go from a 3x3 input matrix to a 2x2 matrix, yeah? Yeah. Say it again, yeah, it's a 2x2. Yeah, so you add, yeah. So this is the matrix which you see here. This is your output from convolution. So this is the output. Now, there's one thing I wanted you to pay attention to, because that introduces another hyperparameter, which is called padding. And if you now look at the values which you have in these specific cases here, if you take the corners, if you look at x0, so let's just mark x00. So this specific value here, this one, appears only here. If you just look through where you have encoded information x00, it just appears in only this block. If I, on the other hand, if I now look at this value, you will see that this one appears here, it appears here, it appears here, and it appears here. So that means that we are carrying with us information about the image in basically all the elements which are now being convoluted. This is something which we often want, so that the information about the image is kept in many different places. If this could be an essential part of your image, this is something you would like to have there. Now, if you look at x01, on the other hand, x01 is something you would find, if we now just look at where we find x01. So if we take that one, this one appears here, and it also appears here. So that means that there are two slots where x01 appears. But if you take x02, that appears only in one place, and that is, let me see, where do we have x02 here? That appears only here. So you see the corners, they actually appear in only one of these slots when we've done the filtering. So what is common to do then is actually to increase the size of this one by adding zeros. So you could add zeros around here. So you could make a padding. This is the padding. And you just fill it in with zeros. If you do that and you perform the convolution, then there will be zeros here. But that means that x100 would appear in more places. Now, the example which we are going to go through, hopefully, gives you a better mathematical intuition of what's going on. So we are going to look at a polynomial multiplication, which when we want to make it efficient, we would have to add zeros to the ends. So hopefully the example which comes in just a few moments is going to help you to see why this padding is very useful. But you see now that some of the information is only retained in some specific parts here, like this corner here, or this corner, which is appearing only here. This corner, which you see here, x20 is only here. Then x22 is only appearing here. Yeah?
And why is there only a plus sign on the bottom left corner?
Plus. This one? That one? Oh, yeah. Oh, yeah, for all of them. Oh, yeah, no, I see what you mean. This is just a slip of pen from my side. So there is a plus. Thanks. This is just me. That's a slip of pen. Sorry, guys. Okay, that's good. There are people with eagle eyes here. Good. So if you now look at what we have done, if we now have a bias to the filter, if we now think of the total parameters with a bias, which is typical to introduce as an additional parameter in case your weights by accident are 0, then we have 4. So these are the weights. plus 1 parameters to train by backpropagation. So it means that after you've done the convolutional stage and you feed it through a neural network, you do backpropagation on a neural network, and then you step back to the convolutional part till the input part. And then you go back and forth till you have reached a satisfactory reproduction of the data. So if you now want to look at this in a broader picture, so what we could say now, suppose now that n is the dimension of the columns of x. So we're assuming that x is an n times n matrix, which is pretty common for an image. You have 200 times 200 pixels. So often for imaging, these images are actually given by square matrices. And then what I'm going to call F, that is the dimensionality of the matrix W. So the matrix W is actually an F times F matrix, F for filter. And when we then calculate the dimensionality, so the output dimensionality, when we've done the filtering, this is actually given by, and if we call this dimensionality for N2, so we started with N, this has a formula which is given by N minus F divided by the stride. So you can actually quickly understand why you divide by the stride, plus 1. So in the example which we had here, what we had then is that N1 was equal to 3, F is equal to 2, and S is equal to 1. We had stride 1. So that means that N2 is equal to 2. So that means the output is a 2 by 2 matrix. Now, if we add padding, as you will see later in the example which we have, with padding, which you normally include because you want to avoid for efficient, because later when we are going to show how you implement this numerically, you're going to implement this as matrices times vectors, and then you want to calculate this efficiently, and then it's pretty common to add this padding. So if you add padding to the, with padding, P, then the dimensionality of this N2 here is then given by N1 minus F plus 2 times the padding, because that increases the size of the matrix. And then it's divided by the stride plus 1. So you would typically have 1 at each endpoint here. And that's why you have 2 times P. So in that specific case, which we had a padding equal to 0. We had F equal to 2, N1 equal to 3, and then S equal to 1, and then we ended up with a 2 by 2 matrix. So let's just take another example to train ourselves a little bit and see how many parameters we need to train in the convolutional stage. So suppose now that we have N1 equals 32, and we have an input volume. So this is the image itself with colors. And we could think of this as a 32 times 32 bits image times 3. So that's the input which we have. And suppose now that we want to make 10 copies and we perform a filtering with a filter which is 5 by 5. So we want to make 10 copies through a 5 times 5 filter. And we could now say we have a padding P equal to 0, and we use this stride equal to 1. So that means that what we are going to get then is a downsized image N2, which is going to be equal to 32 minus 5 divided by 1 plus 1, and that gives us 28. Now, if I then look at the parameters I need to deal with, so if I make the replicas, so in total, what we are going to get then is 28 times 28 times 10 replicas, and we have left out the color channel now. If we look at the training, so if we include the color channel with colors, what we end up with then is we have for each filter, then we have 5 times 5, and then we have the color channels times 3, plus 1, which is equal to 76. So this is the bias. In total, 76 parameters to train. And that means that if we now take the 10 images, so with 10 images, we have in total 760 parameters, which we would train by backpropagation. Okay? And so you see quickly this increases the bigger the image and the more parameters you need to train. So each image then has its own filter and weights and biases. And these, you can decide whether you want to make replicas, which is pretty common. And these replicas could then represent different types, different parts of the image. And then you can now decide whether you want to feed this into a neural network after you've done pooling and relo, or whether you want to do a further convolutional stage. So you can actually repeat the stages again and again. Hope you see the basic philosophy here, right? So if we want to summarize this part here, what we end up with is a new set of parameters. So typically what we will have then, so we require, in addition to the training, so we require 4 new hyperparameters in the training here. And these are set by you before you start training. Yeah? Yeah? Because now I included the colors. So with it, if I have the color channel, then I have to, yeah. So you would have to include that one. So in here, I would also have to have 3 here, right? I just took it away. So I just said with colors, then you would have to multiply everything with a factor of 3. So if you now look at the total set of hyperparameters you end up with, what you would have is, this is something which is set, the minus k, which is the number of filters. So this is part of your architecture, right? So you decide how many times you want, how many replicas you want to make of an image. Then what you need then is obviously the spatial extent of the filters. And I'm skipping colors because this is something you would just have to add in addition. So if the filter is a 3 by 3, F is 3. Then you need to define S, which is the stride. And then you need to define P, which is the amount of this padding. Now, in general, your image is normally a square represented by square matrix. But suppose now it's not a square matrix. Then you would have to look at the width and the height of the object which you're feeding in. So if you want to make this a little bit more general than just a square matrix, then what you could say then is that the input volume, we could make this a little bit more general. And I'm going to write that one as a W1, which is the width. So this is the input. That is the width of your object times H1, which is the height of the object, and times D1, which is the depth. So this could be the color channels. But it could be something else. If you're dealing with a regression problem and you're having, say, 3-dimensional data, you could have a data set which represents the coordinates of the systems, and then some 3-dimensional variable which is also needed, etc. So these are just a more general way of setting up what we have here. So that means that we would produce then an output, which is going to be given by W2 times the height times the depth. And this W2 is normally given by the initial width minus F plus 2 times P, the padding, divided by the stride plus 1. So these are the typical formula which you would set up when you're defining the dimensionalities which you have to deal with. It's pretty common to have square matrices as input, but they don't need to be square matrices. So typical choices, and now it's time to take a small break. I just wanted to summarize that. We mentioned that last time. Typical choices, typical, let me just write it correctly here. Typical choices, which you will encounter in many applications. And the code examples which I'm showing you are actually examples which I have borrowed, like the TensorFlow code on the CFAR data. That's a code which I borrowed from a colleague of mine. And you will see there that you will find different types of options. So F equal 3, stride equal to 1, and P equal to 1. The number of filters you make is something you have to decide. So I'm just leaving that open, K. Another typical choice is F equal to 5, S equal to 1, and P equal to 2. So these become hyperparameters which we actually need to tune when we are running the calculation. And P is equal to open. So you can choose whatever padding you want. So this is about the parameters which you fix before you're setting up the calculation. This also adds parameters like your learning rate in the backpropagation when you calculate the gradients and update the gradients. And it also includes additional hyperparameters which you would have in front of the weights, like an L1 or L2 norm. But you have to set up the architecture, and when you do the architecture in the filter stage, these are the parameters which pop up, which you have to fix. Then you need to decide in the ReLO stage or the detector stage what kind of activation function you want to use. And that activation function has also hyperparameters. If you think of something like the rectified ReLO, that has a small part when the input is negative, which is then scaled by a parameter. And that's a parameter which is set. So there are many more parameters than you have in a typical neural network. And the way we proceed is to try to play around with different filters. This applies also to different types of filters. There's a very popular type of filters which are called Fourier filters. And this field contains a lot of what we might call hand tuning. And the hand tuning is done based on the kind of images which you have. So after the break, we are going to look more into pooling and also this ReLO stage, but we're going to look at an example which hopefully gives us a little bit more intuition about the mathematics of convolution. So that's something we will do after the break. Now you guys have been so kind here that we need to have a small break. Okay. So let's get started again. Okay, so welcome back, everybody. And what I want to do now is to, in a way, baby step you through a one-dimensional convolutional problem. And when we do that, you will also see why padding is a useful feature, which we introduce in the calculations. So the topic I'm going to, or the example I'm going to go through, is the exciting multiplication of two polynomials. This is, I hope you don't get offended by this pretty simple problem. So let's look at the convolution stage itself. And when we're done with that, we are going to look at how we do the pooling and the so-called detector stage. And most likely we will discuss the codes in more detail next week. So today I just wanted to go through some of the mathematics here. We also have people who want to present project variants right after the break. So if you have the possibility to remain, there will be additional projects which will be presented today. But let's now look at the convolution itself. And through a simple example. And this is a one-dimensional case. And then we are going to expand this to a typical two-dimensional case, which is the standard case which we encounter when we look at images. So in this case, I'm having a polynomial multiplication. So I have a polynomial here, which is given by some parameters which are known. A1 times t plus alpha 2 times a t squared. And then I have a third order polynomial, which I call with a beta 0 plus a beta 1 times t plus a beta 2 times t squared plus a beta 3 times t cubed. And these parameters are known. Now, if you then look at the product of these two, which we are called z, which is p of t times s of t, this is nothing but a new parameter, delta 0, plus a delta 1 times t, plus a delta 2 times t squared. So this is going to be a, obviously, fifth order polynomial, since we are multiplying a second order with a third order polynomial. Now, if you look at this example here, you see now that when we do these multiplications, and this is something you may have seen in courses in programming and numerical mathematics, you don't do a polynomial times a polynomial. That is very inefficient to do. So you actually would rewrite this in a more efficient way, and this is what we're going to discuss now. But let's look at the parameters. So it should be pretty clear that this delta 0 is actually alpha 0 times beta 0. That's the first, the 0th order term. And then we have a delta 1, which obviously has to be given by alpha 1 times beta 0 plus alpha 0 times beta 1. I hope you don't get offended if I go through this simple case here. Huh? But I'm going to use this again and again. So these are alpha 1, beta 1, plus alpha 2 times beta 0. And then I can continue. Yeah. Oh, sorry. Yeah, I should do that. Okay, thanks. Then if I continue now with delta 3, delta 4, and delta 5, it should be pretty obvious what these look like. So is it okay if I just switch? Everybody's gotten it? So if we have a delta 3, which is now given by an alpha 1, beta 2, plus an alpha 2 times beta 1, plus an alpha 0 times beta 3. And then I have a fourth order term, which goes like alpha 2 times beta 2 plus alpha 1 times beta 3. And then finally, we have an alpha 2 times a beta 3. If you look at the alpha i's, they are 0 except for I equal 0, 1, and 2. And the same with the beta i's, they're also 0, except for the cases where it's 0, 1, 2, and 3, since this is a third order polynomial. Now, I could write this in terms of the mathematical definition of convolution. So I could now write this delta j here in a very compact way, and I could let my sum run from minus infinity to plus infinity. And I could rewrite it like an alpha I of beta times j minus I. Okay? And you will see that if you plug in that formula, you're getting back these expressions. But now we are summing in a brute force way from minus infinity to plus infinity. And this is what is mathematically defined as the process of convolution. So we would write this as an alpha, and then we have this convolution sign times beta, and then with a subscript j. So this is convolution. When we are looking at a discrete set of variables, if you have continuous variables, this is given by an integral. So you've probably seen something like this in the literature. So if I have, let's say, an output y of some function t, this could then be given by an integral where I integrate over s in a specific domain. And then I have my s of x. This could be my input variable. And then when I'm dealing with imaging or analysis of sounds or similar topics, then I would have an integral which goes like this, where I'm filtering out. So this w is a filter. And we would write this as x times w. So that's the convolution. In this specific case, you could think of you measuring some kind of continuous variable, and some of the measurements are a little bit faulty, and you want to filter them out by this quantity w. So w acts as a filter. So if you have a continuous variable, this is the equivalent of this discrete equation which we put up. Okay? So that's a definition of convolution. Now, how does this enter in this kind of imaging, and how do we actually encode it in an efficient way? Now, one thing, if you look at this expression which we put up here, this is not very efficient because we are just making a sum from minus infinity to plus infinity. So we have a huge sums, and we're going to collect lots of zeros. Now, if you look more carefully at this one, this is something which you can rewrite like a matrix times a vector. Now, one thing is that the process of convolution is what we call commutative. So that means that I can interchange alpha and beta. But if you look more closely at this one, and now you want to avoid summing freely, what you could do now is to say that these parameters delta are now given by a vector. So let's look at delta. And now this is a vector, so I'm trying to make it bold-faced. And I could write it out like this. So I could write it out like an alpha 0, 0, 0, 0. And since my object beta is a vector of length 4, I'm actually going to have a matrix which is going to have length 4. Delta has length 5. So I should have 5 rows and 4 columns. And this is why I'm setting it up like this. So I'm going to have an alpha 1, alpha 0, 0, 0. And then I have an alpha 2 of alpha 1, alpha 0 of 0. And then I have 0. And then comes alpha 2, alpha 1, alpha 0. And then 0, 0, 0. And then I have an alpha 2 here. And that is multiplied with the vector beta. And you would see that when I perform this multiplication, I'm actually going to get those terms which we put up. So I will get a fifth order term. So this is one way of actually rewriting it. Now it's commutative, so I can actually interchange a matrix for alpha with a matrix for beta. So I can rewrite this. So if you perform the matrix vector multiplication, you see now, just to give you an example, I have alpha 0 times beta 0. That is going to give me delta 0, as we saw here. So this is delta 0. If I look at my next row here, I have alpha 1 times beta 0, alpha 0 times beta 1. And then I go back here, and you see that delta, so this should actually be delta 1 here. Sorry for that. There, no, sorry, that is delta 2. I was looking at the wrong entry here. So this one is what I would get if I now perform this multiplication with this vector. So this is a more compact way of setting it up, and it's more efficient. But you can, since the process is commutative, I can interchange alpha and beta, and then I can get a smaller matrix. And that leads normally to less floating point operations. So these kind of manipulations are actually being used. So I could rewrite this delta as a matrix which is 5 by 3. So I have beta 0, 0, 0. I have beta 1, beta 0. And I have a beta 2, beta 1, and beta 0. I have a beta 3 over beta 2 times a beta 1. And then I get 0 of beta 3, beta 2 here, 0, 0, and then I have a beta 3. And then I multiply this one with alpha 0, alpha 1, and alpha 2 here. So again, if I look at the first row here, multiplied with a vector, you see I get beta 0 times alpha 0, and that is delta 0. If I take the second one, I get beta 1 times this, beta 0 times alpha 1, and I get back what I have. So this is a very compact way of encoding this type of convolution. And when we are, if you look at this example here, you will see that we are going to replicate it when we are doing the convolution on images, for instance. So that type of matrix, there's actually a whole field in mathematics which uses this type of matrices. These are called tuplets matrices. And some of you may have encountered them in the solutions of linear equations. And this is a sub-discipline in mathematics itself. And the mathematics of these tuplets matrices, without us going too much in detail, is something which is being exploited in the setup of convolutional neural networks. So if you wish to dig a little bit deeper than what I'm offering you here, then take a look at the theory of tuplets matrices and convolution. But in general, a matrix, if you now look at such a matrix, which we call a tuplets matrix, let me just give you an example of one. So let's call this a matrix A, which now has specific elements. So it has an A, 0, 0. And you will see now that it's pretty close to what we had previously. So it has an A2, A1, A0, and then it has an A3, A2, A1, 0, A3, A2. So this is the matrix actually where we label everything with beta. So this is a typical tuplets matrix. And what you will see is that these diagonal elements, AII, are often written in terms of AI plus J, comma, over J plus 1. And they are supposed to be the same as A of J, of AI minus J. So this is a so-called tuplets matrix. Now, the thing which I wanted to discuss with you now is how do we implement this efficiently when we are dealing with a convolution with respect to convolutional neural networks. So if we now look at this example which we had with a polynomial multiplication, what I'm going to do now is to replace beta with x. So this is the input which we have. And normally, your input matrix has a larger dimensionality than your filter. So it means that if you look at x here, and we look at this case which we have, beta has more elements than the vector alpha, because beta represents a third order polynomial, whereas alpha represents a second order polynomial. And then I replace this alpha with W. So that is my filter. And normally the dimensionalities of W is smaller than the dimensionality of X, the input. And then what I do then is to replace delta with Y. So that is the output. Then I can actually write one of these numbers, Wi, and I'm trying to use this more matrix vector notation. So this is given by the convolution between x and w for element I. And that is defined when we now look at this specific example as a k equals 0 up to k equal to m minus 1. And we can write this in a compact way like w of k times x of I minus k. And in our case, m is equal to 3 because we have this vector w. So w contains now w0. This is now representing, in this specific case, a second order polynomial. So it has 3 elements, right? X is a third order polynomial, and then it has 4 elements, okay? So x is then simply given by x0, x1, x2, and x3. So this will be the same as we had before as alpha 0, alpha 1, and this will be alpha 2 here. Now, if you now look at what we are doing here, there is something which happens which is unwanted when we implement. So this is another way of writing the convolutional process. So if you look a little bit closer here, when I put k equal to, let's say, 3, and I equal to 1, I get of x minus 2 here. And that's something which is not defined. So if I define a vector for x, I would define it with 4 elements. But if you look at the formula here, when I put in an I here for, let's say, 1, and so I equal to 0, and k is equal to 2, because m is equal to 3. If I do that, I will get an element which is x minus 2, which is not defined here. Okay? But there's nothing which hinders me to increase the size of x by padding. So this is how you can see how padding comes in. So we just extend the size of the vector so that we have defined these elements. Because if I were now to encode this, I will get an error message in my program saying that you are trying to access an element which has not been declared. So that element doesn't exist in your memory, and then you will simply get a segmentation fault when you run your program. So what you do then is you simply increase the size of the array and rewrite it by adding 2 points at each endpoint. So let's see how we can do that, because this also shows us why padding is an important feature when we're doing this type of operations here. So if you now look at what we have here, is that for specific values, for specific values of I, we get, or we have to fetch x minus 1 and x minus 2, which are not declared. So since my sum runs for the parameter which I have here, the variables k, they are defined in terms of these 3 ones. So that runs from 0 to 2. X runs from 0 to 3. So we have 4 elements. So the thing which I would do then is actually to add parameters. So what I can do is to increase the size of x, so that n, which previously was equal to 4, is now going over to n plus 2p, where p is my padding. So p, in this specific case, is going to be equal to 2. So I'm going to define an x0. This is a new value, which is 0. I'm going to define x1 equal to 0. I'm going to define x2 now, which is equal to the original value, which then was my original x0. Then I define my x3. So these are the specific values which we had previously. I have my x4, which is then equal to beta 2. Then I have my x5, which is going to be equal to my original beta 3. But then I have an x6 and an x7, which I'm going to put to 0. So I've added two elements at the two endpoints. And in that case, I can actually rewrite my summation in a compact way, and I will not enter the problem of segmentation fault because all the elements have been defined properly. So what I would do then is to rewrite this y of I in terms of a sum over k equals 0. And then this k goes up to m minus 1. And I have a w of k. And then I have my x of I plus an m minus 1 minus k here. So I'm just rewriting the sum, and I avoid the problem of not having elements which are undefined. So my parameters, which I'm ending up with now, if I now look at a case with y equal to 4, that is going to be given by x6 times w0 plus x5 times w1 plus x4 times w2 here, the original ones. And when I go back and fetch the parameters which I have in these different arrays, I have 0 times alpha 0 plus beta 3 times alpha 1 plus beta 2 times alpha 2. And these are the values which I have encoded already before. You see how I can rewrite this in a very compact way, which is computationally more efficient and it avoids segmentation fault. So the only thing I add is actually to add some zeros to the two endpoints. And then I can perform the operation without thinking. Because I'm sure that I won't hit any of the segmentation fault problems. If I look at this y of 5, which is then equal to x7 times w0 plus x6, which were both x7 and x6 are actually 0, times w1 plus x5 times w2 here. This is nothing but two zeros multiplied with w0 and w1. And this at the end becomes alpha 2 times beta 3, which is what I wanted. So this gives us a very compact way of performing these operations. Now, one way you also redo things is to rewrite this more efficiently so that you don't need to have this specific loop, but you can write it as a dot product between two vectors. So what I could do then, if you look at the expression, if I redefine W to a vector W tilde, and then this W tilde is so defined that W tilde 0 is equal to the original one. W tilde 1 is equal to the original one which we had. So this was the same as beta 2 here. No, sorry, alpha 2. No, not alpha 2 here. And this is the same as alpha 1. And here I redefine 2 here to be equal to the original value 0, which is then alpha 0. If I do that, then I can rewrite everything as a vector in a product. So then I can rewrite, that means that this y of I here can be rewritten as a standard dot product between two vectors, where the vector x goes from I to I plus m minus 1. So this is just a patched element of the size m, and this is then multiplied with w here. So that gives a very efficient way of performing the convolution, where we also motivated padding in a slightly different way from what we did in the previous lecture. In the previous lecture, we motivated also padding from the fact that some of the points which we had in the image would only appear in only one point of the final filtered image. And here you see also that there is a computational aspect which allows us to avoid multiplications with quantity which are not defined. Any questions so far? I hope this example shows you a little bit of the way we practically implement these convolutional processes. And what I want to do now is actually to go back to the Jupyter Notebook, because I have an example on how you can rewrite a matrix which is given by your image, which defines your image, multiply with a filter in a very efficient way. And that's the way you would typically implement it numerically. So let's go back to the Jupyter Notebook and take a look at the way we would do filtering when we are dealing with matrices. So this simple polynomial multiplication is something which is meant as a way to illustrate how you do the convolution. So some of you may have studied things like Fourier series. So how many of you have done that? So Fourier series are examples of where you do convolution. And you probably met then the mathematical definition of convolution through Fourier series. Does that ring a bell? I can see some people nodding here. That's a very common field where you would encounter the mathematical operation of convolution. And it's very much used. Fourier series are very much used in analysis of time series and also in images, sound files, etc., etc. So if we scroll down a little bit, you will obviously see many of the same things which we have discussed. So here's an image which I took from Rashka's textbook. And this represents a typical process where you now have a convolutional stage where you reduce it down. You actually make 32 new images. You have a black and white image, 28 times 28. You scale it down. And then you have a pooling stage where you reduce further dimensionality. There's a new convolutional stage. You will see now that many of these numbers of images or replicas you make, they are typically given by binary powers of 2. So typically they would go like 16, 32, 64, 128, 256, etc. And then after the pooling stage, you end up with a flattened object, which you then feed into your convolutional or your standard neural network, which is this one. And that ends up, if this is the MNIST data, which I'm using in the examples here, you have 10 numbers. So your final output layer is given by the softmax function, which then is used to classify whether this is number 0, 1, 2, etc. So you have 10 classes, 10 handwritten numbers. So this is just a quick repetition here, but let's look at an example, and then actually maybe I'm going to go back to the other one because that. But let me just go down a little bit. So you will find these examples which we have discussed here now in the notes. So this object is something we went through. So when you have a two-dimensional object, which is a pretty common one, the way you would do the filtering is given by this equation here. So you have your X, your input, then your filter, and then the output Y here. And this is just the two-dimensional variant of what you saw previously in one dimension. So if you've gotten the picture with a one-dimensional case, you just need to extend this to 2 dimensions or more dimensions. And dealing with tensors or matrices, depending on the type of problem which you have. So you can rewrite it like this, since it's a commutative process. And if you look at this as an example, this is the example we started with. And this tells you a little bit about how you actually do these calculations. So you would have an input here, and then this is the filter. And when you perform the operation here, this is the way you would just put it in. And when you do that, you get this expression which we put on the whiteboard in the previous lecture. Okay? And then clearly one thing you see is that this X0 appears only one place. So adding padding is something which then can make X0 appear in more of the columns here and rows. Why? Because if you see now, if you carry with you the information about a specific part of your image in just one place, that the information through the different filtering may play a less important role. So if you want this to be important, you would have to have it carried with you. So suppose this X represents the corner of a house, and you have it only one place, then you miss information about the corners. Because many of these filters are really hand-tuned to specific problems. And you will see that, especially in the project you guys are going to do. I mean, tuning the filters to the type of problem you have is an important topic. And in this case, you can actually rewrite this in a different way. So this is the way we just put it up here. But you can actually think of this matrix X being flattened. And you can flatten it out. If you look at the matrix, instead of having it as a matrix, you can flatten it out as a vector. So that means that your vector goes like this. So you have the first row, the second row, and the third row. So whether you want to represent it as a matrix or as a vector is very much up to you. Now, if you do that, you can actually rewrite the problem which you have in terms of a matrix vector multiplication, where you define a new vector where you flatten out the input as a vector X prime of length n, and you have the filter, which is a matrix of dimension 4 times n. So you could write a filter like that. In that case, you can then rewrite everything in terms of a matrix W times a vector X. And this is then when you perform the multiplications here, which is a vector of length 4, because you have a matrix of length 4 times n. You have a vector of length n, and that gives you obviously a vector of length 4. And the final matrix, so this is just you flattening out the matrix to a vector with 4 elements, which then corresponds to a 2 by 2 matrix. Okay? So this is typically the way you would now encode this when you're setting up the filter process. And this is something we will discuss next week when we're going to look at the codes for a convolutional neural network. So that just to give you the kind of mathematical operations which are present in a CNN. And then the parameters, you would train them by the backpropagation. So you have to train these parameters by setting up the gradients and all the beautiful gradient descent methods which you have available, and then train the parameters that way. So this is also a repeat of what we had, but I wanted to say something, so we discussed this, but I wanted to say something of about the filtering here and the padding. So you can see examples of padding here. This again, an image which I took from Rashka. So you have a kernel, which is a 3 by 3. You can have an input, which is an 8 by 8 in this case. But if you look at the pooling case, this is a typical process you would use to reduce the dimensionality. Suppose now that you've done the ReLU stage after the filtering, and then your output looks like this. So there are blocks of 3 by 3. And you have to decide then on how you want to do the pooling. So a pretty common pooling is to have a 3 by 3 blocks. You can have 2 by 2 blocks. And you will see that in the input to TensorFlow or PyTorch, how you set up the pooling blocks. So what you do now, if you have a 3 by 3 block, you can, 1, pick the largest value, which is 8, or you can take the average of all the elements, which in that case is 3.78. So if you do that, if you have these 4 3 by 3 blocks, so this is actually a 6 by 6 matrix, what you can do then is to reduce this to a 2 by 2 matrix, where you then keep the largest values. So this is one way to keep or reduce the dimensionality, but just keeping the largest values, assuming that the largest values are the most important ones. So this is the pooling stage. And when you've gone through this, the convolution part, the ReLU part, and then the pooling, that is one convolutional step. But then you can repeat this and you can make more replicas, new filters, and then new pooling stages. And at the end, you have many replicas, which hopefully contain information about different parts of your image. When you make these images smaller, then it's much, much simpler, actually, from a computational point of view, when you set up your standard feed-forward neural network. Because the feed-forward neural network implies you doing matrix-matrix or matrix vector multiplications. And if your matrix is huge, if you have, as I said in the beginning of the previous lecture, if you have a 200 times 200 pixels, and you have 100 nodes in the first hidden layer, your matrix with the weights to determine is 40,000 times 100. So that's a pretty large dimensionality for the number of weights you need to train by gradient descent. If you, on the other hand, have reduced all these images and made replicas, obviously, the dimensionalities of these matrices are much smaller. And then you can actually grind them through a standard matrix or matrix vector multiplication. Okay? That sound okay? Good. So I actually wanted, if I have some time here, I wanted to go back, but maybe we take that next time. I wanted, so in the days before you started using deep learning methods like convolutional neural networks, the common strategy was to use the singular value decomposition. So there is an example here on how you can compress the size of an image. So you would then store only that compressed image, but you would have, in order to be able to reconstruct it, you would have to keep track of the singular value decomposed vectors and the singular values themselves. So I see I'm running a little bit out of time, and I thought we could start a little bit earlier after the break so that people who want to present can do that. So I will pick this up next week. And next week, if you scroll down the slides here, you will also see the examples on how you can use TensorFlow or PyTorch. So I actually put up two examples here. So this is again the MNIST data set. There is an example with TensorFlow here, and you can follow that one. And after that one, you will find an example with PyTorch. And after the PyTorch example, there is an example of how you can write your own code. And then we are going to go through these different steps with backpropagation, setting up the filters. Because when you use TensorFlow, as you can see here, you can now set up the pooling layers, 2x2 pooling matrix. You can set up the regularization. You can set up the convolutional stage here and defining the parameters which are putting in. You can define how many dense layers you want. And then you have also an activation. This is the output layer. So we are going back to this next week, and we are going to see how we can do that with PyTorch as well, in addition to you writing your own code. That was a group last year which did that. And that's a project by itself, if you want to build it from scratch, which will keep people busy a whole semester. Okay, so we do a short break, and then I know that there's a Carl Frederick and Jonas who wanted to present something. If somebody else wants to present, then feel free to do that. But we just take a short break, let's say 10 minutes, and then we bring up the example here. So I'm going to stop the recording, but I'm going to